Step lap joint of the core. Transformer usually consists of the core and the winding. To reduce eddy current losses in the core, it is made of stacks of thin sheets of silicon steel. To assemble the winding on the core is made demountable. And when you connect different parts of the core together, you cannot avoid gaps. To reduce magnetic resistance of these gaps, the step lap joint was invented. Here you can see a piece of the core. There are 12 sheets with a sheet thickness of 0.5 millimeters. And here you can see the air gaps. In the step lap joint, the gaps are distributed to reduce the magnetic flux fringing. So our task is to calculate the magnetic field distribution and locate spots with high saturation level. AC magnetic flux density is 1.9 Tesla. Okay, let's start QuickField now. In QuickField I create new problem. Problem name is joint. Next. Problem type is AC magnetics. Frequency is 50 Hz. Model class is plane parallel. Length units are millimeters. Finish. On the left you can see the problem pane, and on the right you can see the geometry model editor window. You can draw the geometry model here, or you can import the geometry model from the AutoCAD.exe file. The model is simple, so I will draw it here. Switch to the insert mode. First I will draw the rectangle, some 40 millimeters in length and 0.5 millimeters height. Insert. Now let's zoom to fit. Next I will draw the air gap. The gap dimensions are 0.5 millimeters by 0.5 millimeters. This will be the air gap. So this is only a single sheet of steel with the air gap. And I need 5 more copies of this sheet. Switch to select objects mode. Select everything. Edit. Duplicate selection. Remember, we simulate the step lap joint, so the gap is distributed. So I will specify some displacement along the x-axis. -2 millimeters. And the sheet thickness is 0.5 millimeters. In fact, there is a teeny insulation layer between sheets with a thickness of about 1 micrometer. So I will increase the displacement by 1 micrometer. And I need 5 more copies. Okay. Now I will zoom to fit, select everything, and again use the duplicate operation. This time I will just make another copy with the vertical displacement. 6 sheets will be 3006 millimeters. Okay. Now you see the pattern. In fact, the sheets are long, and I will draw lines to limit the simulation area. Switch to the insert mode and draw the lines. And I will delete the unnecessary parts. Switch to select objects mode again, select with the rubber band and click delete. Yes. Delete. Yes. Okay, the geometry model is ready. Now we should assign labels. Through labels we will specify material properties. I select again with the rubber band. This would be the steel sheets properties, and here I type in the label for the blocks. Steel. Okay. You see the label appeared in the tree. Now these would be the air gaps. Properties, air. And we have the air here and here. Properties, air. Okay. Remember, we have the insulation between the sheets, so I will zoom in and again use the rubber band to select the spacing between the sheets. Properties, this would be insulation. Okay, the same way for the other spacing between sheets. Hold the Ctrl button pressed to select multiple objects at the same time. Now I have selected all the insulation layers, open the properties and select the label insulation. Okay. That's all for the blocks, but we should also assign labels to boundaries. I will use boundary condition to model the external magnetic field. So I will assign and label bottom at the bottom edge, and I will assign label top at the top edge. Now let's specify physical properties. For the air, I specify relative magnetic permeability of 1 and nothing else. The same for the insulation, 1. For the steel, I will specify the BH curve, which I have already prepared in the Excel file. So I will just select the data, copy, paste, and here you can see the curve. Okay. To specify the external magnetic field, I will assign 0 magnetic potential at the bottom edge, and I will specify some linear current density at the top edge. In fact, I already simulated the problem and found out that the linear current density should be 90 kiloamperes per meter to produce the required field of 1.9 Tesla. Before I start the analysis, I should build the finite element mesh. In fact, I would like to adjust the mesh spacing manually. You see, we have the very small gaps, and QuickField might try to build the very dense mesh. So I will select the core, open the properties, and here I will adjust the spacing, switch to manual, and specify the spacing value of 0.1 millimeter. Okay. And for the top and for the bottom edges, I will specify the spacing of 2 millimeters. Now let's build the mesh. Save all simulation files and run the analysis. The problem has been solved. Let's take a look at the results. Here you can see the field lines. You can adjust the field picture and switch on the color map of the flux density. You can see the correspondence between the color and the value in the legend. Let me check the flux density exact value in the core. I will use the probing tool, click somewhere in the steel parts, and here is the flux density. There is another option to measure values. I will use the contour tool, draw the contour line here, and get the flux density distribution on the XY plot. Indeed, the flux density is about 1.9 Tesla. And I can use contours to calculate integral values. Click the integral calculator. Here I can calculate the magnetic flux, I can calculate the contour length, and if I draw the contour along the core from this point to another point, I could see how the field is expelled from the core. Window tile horizontally. Now all these spikes are located just above the air gaps. Now let me see how can I visualize these spikes on the color map. Properties, I will switch on the field strength and switch off the field lines. Okay, let's adjust the scale. Now that's better. Now you can see the places where the field is expelled from the core. Now let's locate the spots with the high saturation levels. Again, I will adjust the field picture and switch on the color map of the magnetic permeability. And I will adjust the scale, set the maximum value to be 100 and the minimum value to be 20. And I will also switch on the vector plot of the flux density with the spacing between vectors of 0.25 millimeters. Okay, now let's zoom in. Now we can see that the saturated parts are located in the steel sheets adjacent to the air gaps, and the magnetic flux have to jump from one sheet to another to avoid the air gaps. QuickField has many tools that can help you to visualize magnetic field in the joint. You can compare different designs of the joints on the basis of the stray flux value or magnetic permeability distribution. If you search for the step lab joint on our website, you will find the example page. Here you can read about problem setup, browse the solution section, take a look at the resulting pictures, and you can download the simulation files here. Simulation files can be opened and the results may be viewed using any QuickField edition, including QuickField Student Edition that you can download from our website for free.